Hi, my name is Abrar, and this is Lab 5, Faraday's Law. Introduction. So Faraday's Law relates time-varying magnetic field to a Curly electric field. This current, in turn, produces a magnetic field which exerts a force on the source of the external magnetic field. In this lab, the source of that external field is a falling bar magnet, and the induced current is driven in a tube of aluminum foil. In this lab, we will collect observational data of a magnet falling through a conductive tube of aluminum foil, model the magnet-tube interaction computationally, and compare our computational predictions with our observed data. The physics principles in this lab are the magnetic field of a bar magnet, the magnetic flux and derivative with time, Faraday's law, magnetic force on a falling magnet, and Lenz's law. The materials required in this lab is a smartphone, a bar magnet, a magnetometer app, a roll of aluminum foil, a meter stick or ruler for measuring the dimensions of the tube, and the distance it traveled. The procedure. So first, we mark the north pole of the bar magnet. We set up positioning of magnet and tube along with recording. We start recording and drop the bar magnet. We observe the video to find enter and exit times. We repeat this whole process 5 times and then average them. On the right, you can see the data collected from this lab. So the length of the tube we found was 0.31 meters. The width of aluminum foil was 0.006 meters. The inner radius was 0.02 meters. The outer radius was 0.027 meters. The mass of the magnet itself was 0.024 kilograms. The average time taken was 1.25 seconds. And the theoretical time, which was what we calculated to be, was 1.32 seconds. So here's the code for our experiment. So in step 1, I included measurements from the previous data collected, including the length, width, inner and outer radius of the aluminum tube foil. In step 2, I wrote the function for the magnetic field of the bar magnet. In step 3, I calculated the magnetic flux function, and for step 4, I calculated the current in the ring. For step 5 and 6, I found the magnetic field at each ring. And then in steps 7 and 8, I dealt with the magnets themselves. So this included the net force on the magnet exerted by the system, as well as the magnet's velocity and position. So the discussion questions: interpreting the simulation. Which color corresponds to clockwise current as viewed from above, and which one counterclockwise? So I found the red to be clockwise and the blue to be counterclockwise. What happens to the dynamics of the system when you flip the magnet around? So when you flip the magnet around, the motion stays the same, but the current flips. How does the total time in tube of your real-world system compare to that of your computational system? How might the computational system be made more accurate? So as our computational system does not account for air or conductivity resistance, it is not that accurate. What does the shape of the velocity versus time graph tell you about the forces acting on the bar magnet? So this graph shows that the net force is 0 and that the bar magnet stops accelerating when it reaches terminal velocity. So here's our computational model. On the right is a figure for the tube and the magnet, and on the left is the graph of velocity versus time of the bar magnet. As you can see, the forces are unbalanced in the force portion of the graph when the speed is increasing. The forces are further unbalanced in the opposite direction when the speed is decreasing. And the forces balance just for a second for that portion of the graph. Finally, the forces are unbalanced again as the speed increases. On the bottom, you can see that predicted time taken was 1.32 seconds when the actual time taken was 1.25 seconds. Discussion questions. What if the resistivity of the conductor was reduced as close as possible to 0? How would the dynamics of the falling magnet change? So the braking force increases to the point where it balances the gravitational force and prevents the magnet from falling through to the tube altogether. What if the holes or slots were cut into the tube? How would this affect the ring currents in your model? This would disrupt the normal flow of the current through the rings of current value in the tube. What would most likely happen is the braking force would not be as strong due to a reduced amount of current being able to flow through the tube. Thank you.